Good afternoon. I hope everybody can hear me and see my screen. So my name is Gerrit Tron. I work as a geologist for Datamine software in our Johannesburg office. In this webinar, we are going to work through Studio RM's advanced estimation module using a standard data set. The advanced estimation module is a separate module that runs inside Studio RM. It includes co-kriging, enhanced variography, and kriging neighborhood analysis. Estimation is simpler and faster than the old Estima process, and it can make use of multiple cores in your computer when they are available. Okay, advanced estimation stems from a collaboration between Datamine and GeoVariances, where specialized algorithms are applied in Studio RM in an easy-to-use workflow. For those who don't know GeoVariances, they are an independent software provider in France, which was founded some 34 years ago and who specialize in geostatistics. These high-end algorithms can now be used by resource geologists everywhere, and the Datamine workflow in the module aims to simplify the tasks. And this is what we are going to cover this afternoon. Due to time constraints, can we please wait until the end of the webinar with questions? Then we'll be happy to answer them. If I need to consult with our specialist, I'll get back to you via email. I've also asked my co-worker, Dr. Benny Chisonga, to act as my co-presenter, so he's welcome to chip in from time to time. Thank you for your time, and it's a privilege to have you as my guest this afternoon. Before we start, let's just recap on some of the improvements which was made in the advanced estimation module in recent releases. Okay, let's start with version 1.4. There were quite a number of improvements, as you can see from the slide, and I'm just going to talk about the more important ones. There were some major improvements in the 3D variogram maps, where one can investigate the anisotropy, including auto-fitting of those variogram contours. You can create variograms of normal scores and back transform these with ease. You could apply a rectangular search volume instead of the traditional ellipsoids. Subcell estimation became possible. It was also possible to produce a sample out file, which we can use to investigate which samples were used for which block estimates. K&A results could be opened in a table editor and exported to Excel, so you can maybe draw some of your K&A graphs in Excel for reports, and you can import and export estimation scenarios, which was also very handy. Then in version 1.5, we were allowed to provide a description for each model set. Let me just switch on move my slide. So we could put a little description to each candidate model set, which made it just easier to back reference and remember what you did. You can also now edit domain and variable names of a modeled variogram, which could also be useful, for example, if a zone has insufficient data and you want to use the domain of a different variable, or where you wish to use a variogram for a different related variable to estimate. Variogram models and search parameter files for Estima and Estimate can now be used as inputs to the advanced estimation tool. For those unfamiliar with Datamine, Estima and Estimate are all the estimation processes in Datamine. You can also now choose the maximum number of samples per hole, which may be exceeded. You can also now overlay the downhole variogram with non-downhole variograms in order to get a better understanding of the nugget. The most recent release in 1.6 had a couple of improvements. The most important being, if you use either ordinary kriging or simple kriging, and you use a discretization of 1 by 1 by 1, You can choose to swap from the default point rigging to block rigging. Then you can also define secondary and subsequent search volume passes using the same size ellipsoid, but then you can expand it and you can apply different number of samples. You can generate both cross and normal score variograms in the same estimation scenario. You can save model panels. The Save Model panel now displays whether the candidate model set is transformed or untransformed. And there's an option to apply grade capping for high and low grade values, just to deal with outliers, which is also very handy. As you can see, our developers have been hard at work in improving this awesome tool, and they will continue to do so. Your suggestions and comments are very welcome and will help us to further improve this tool. We've had some great suggestions from clients, so thank you for all those suggestions. It's now possible to record the files, fields, and parameters that we use in advanced estimation as a macro, which can then be used in the underlying co-creek process. Okay, so the macro and data files can then be edited, and the macro can be rerun as the co-creek process. If you need help with this, please feel free to contact me, or even most of your nearest Datamine offices will be able to help you with that. Okay. We are now going to enter Studio RM, and we're going to work through an estimation using ordinary kriging and simple kriging. But before we conduct the estimation, we're going to do the following. We're going to look at some descriptive statistics of our data set. We're going to create 3D variogram maps. We're going to model the variograms. I was planning to do some kriging neighborhood analysis, but due to the time constraints, we're not going to get to that. We might schedule a short different webinar to cover that, maybe next week. Kathleen Hansman, my colleague, also covered it in past webinars extensively, so we can also send you the link to those webinars. So we're going to do all of this in the advanced estimation module. But first, let's just quickly look at the data that we're going to use. Okay, let me just switch my screen to Studio. I'm just opening the project. Okay, there we go. Let me just load the block models of the drills quickly so we can see what we're going to use. And I'm just coloring them by gold. Okay, so that is the data set we're going to use. If we want to quickly query the data, we can run query multiple drill holes. The shortcut is QMD. Let's quickly do that and see if we can get some more information. So I'm selecting all my bore holes. I'm running QMD, and it will quickly give us some information on our drill holes. If we just look in the output window, I can see we've got 153 bore holes in our data set. It lists all of them. Then we can also see the sample length varies from just more than 0.01 meters to 2.5. These bore holes were actually composited at lengths of 2.5 meters. So that small sample length must be some sort of a residual sample. There's only one rock type in these bore holes. We've got a total number of samples of 4,453 samples, and that's more or less just a quick overview of our data. If we go to plan view and we do a quick query line, we can see the samples are more or less 45 to 50 meters apart. So that's the borehole spacing, more or less 50 meters. Okay. We also have a blank block model, which I'm going to load now, into which we are going to estimate the qualities. Just some background information. From my field mapping, I know I've got a dip direction of about 30 degrees. So that's 30 degrees is 90 degrees to the strike. And then I've got a dip of my ore body of between 13 and 18 degrees perpendicular along that dip direction of 30 degrees. Okay, we can also see if we look at the ore body or the drill holes, we can even let me quickly load a section definitions. I just want to quickly show you what the grade looks like in section. Active section, let's flip it. So those boreholes, we can maybe see that the grade sort of follows a dip. And we can look at a couple of sections and confirm that trend of the dip, down dip. Okay, so that's just a quick overview of our data. We are now going to go into the advanced estimation tool. Okay, the advanced estimation dialog or button can be found there on the left hand side in the estimate ribbon. If you hover your mouse over it, it says advanced grade estimation. Let's click open that. Okay, then the advanced estimation dialog opens. As mentioned, this is a separate module and is not included in the standard Studio RM product. You're welcome to contact us or your local Datamine office for a quotation. The separate pricing is unfortunate due to the commercial agreements with geovariances. Once the model opens, we can see the workflow-driven menu on the left. So basically, you would work your way down from the top to the bottom, but obviously you can go back and forth as you wish. Okay, we are going to describe what each of these tasks do as we work through this exercise. All right, the first task that we have is scenario setup. Over here, the user can create various scenarios or estimation runs, each having, for example, a slightly different parameter. This will allow the user to do some testing, investigate what impact changes in some of the estimation parameters can have, or just simply to revert to previous estimation runs. The user can also export and import these scenarios, which is great for standardization, for instance, in a corporate environment, and also for auditing purposes. You can see I've got some scenarios listed here, but let's create a brand new scenario for this exercise. You'll see there's a couple of options: create new scenario, import an existing scenario, create a copy of an existing scenario, load a selected scenario, export a scenario, or delete a scenario. I'm going to click on create new scenario. There's my new scenario. I can rename it. So I'm going to call it webinar 3 and save changes. The dialog box will display the name of the scenario, the samples used, and the model prototype used. At this stage, we haven't assigned any samples or model prototypes to our estimation scenario. Okay, you can see if I select the scenario, I can either load the selected scenario, export the scenario, or delete it. So I'm going to say load scenario. The next task is select samples. We are going to choose a sample file we want to use for our study. In this example, and in most practical real-world scenarios, this will be your composite Borel file. It should be noted that you can choose one file, so you can only choose one file. So if your dataset consists of various files, they should obviously be combined into one file before the advanced estimation process is started. So let's go and browse for our Borel file. We can then select the applicable X, Y, and Z coordinates. We see it picked it up correctly already. We can define the grades of variables which we want to investigate. So I'm going to choose silver, gold, and copper. We can choose a zone or domain field. Notice we can have a domain field zone 1 and zone 2. So zone 2 will be a subdivision of zone 1. The domain field is typically your rock type or reef type or any attribute which distinguishes it statistically from the rest of the population. In this example, I'm just going to choose the rock. Borel ID is picked up correctly, and from and to is picked up correctly as well. It will provide us with some sample summary statistics at the bottom. You can see there is only one zone, one rock type in this Borel file. It contains 4,453 samples, as we saw earlier with the query drill hole command, and it's got 153 Borels in it, with a mean sample length of about 2.45. We can then go to the right-hand side of our screen, and we can say recalculate sample statistics, recalculate sample stats. This provides us with some useful information. Okay. If we look at the statistic, the number of non-absent sample pairs, we can see how many samples there are with assays for each variable. For instance, gold, we can see there's 4,452 samples. For silver, there is 4,058, and for copper, 3,136. So immediately you can see that gold was assayed in all the samples, and copper in about 70% of the samples. We can also look at some other statistics, such as correlation. If we choose correlation, we can see the correlation between silver and gold is fairly positive or fairly good. You can see the green shading in the block at 0.63. So it's positive, and we can say they are correlatable. The correlation between silver and copper is poor, and the correlation between gold and copper is also poor, hence the orange shading. Right. We can see if we click on the drop down, there's a couple of other statistical parameters, the correlation p-value, the covariance, the F ratio, and the paired t-test statistic. These are all tools which we can use to prove that the variables have some sort of a relationship with each other. Okay, I think we all know that if you want to successfully use one variable to estimate another, lesser sampled variable, there must be some sort of a correlation between the two variables. What's more is that we must prove that our assumption that the two variables are correlatable, and this tool makes it extremely easy to do. We can now move on to the next step, which is the variography. So we click on investigate and isotropy. Okay. You can see in the first dialog, we can load an existing 3D map file, or we can create a new one. This will give a default name. I'm going to just rename it to a slightly simpler name. Let's call it 3D map. The next thing is to load, select the domain or zone that you want to investigate. We've got only one rock type, which is rock type 1, so I'm going to pick 1. The variable that we want to use, let's use gold for this example. Okay, we can see there's some information that we get at the bottom there. The lag, which is 60 meters. That is usually about 50. I wonder if I did something wrong now, but that must be usually the borehole spacing more or less. Okay. If you want a better resolution, you can change the number of blocks. It might make it a little bit longer to create the 3D maps, but your maps will have a higher resolution. I'm going to leave it at the 50 meter default. We can then click on Create 3D Map. I'm going to move my estimation dialog to my other screen, just so that we can view the 3D variogram maps, contour maps. Okay, so it opened a new window in Studio called 3D variogram with 4 little sub windows inside the main window. The top right-hand map is very useful as it contains a 3D map of our different contour maps. And we can use that just to make sense of what we are doing. We can see our boreholes are also loaded, so that will also help us to just get a sort of feel for what directions we are going to use. If I go into plan view in that map, I can see my boreholes. I can switch off my map. There's my boreholes, and they are like located in their original position. Okay, so the aim of this is to align the direction of least anisotropy with these dotted axes. So let's start with that. So I'm going to rotate my axis until it aligns with the direction of least anisotropy. We could also change the legend. If you look at the top left-hand corner, there's a Show Legend button with a scale bar. The sill is automatically set to the variance of the data, but you can move the slider up and down just to change this intervals. Okay. You will see there's an auto-fit button as well, which typically asks you to move the scale bar up and down until you've got a solid red area around the center of your contour map. So we're going to quickly align all our axes so that they align to the direction of least variance or least anisotropy. Oh, yeah. We can look in the 3D map just to make sure that our axes, the 3 axes, align to those directions. If I look at that, I can see this red axis aligns to that direction. If I move it around, it does it on that side as well. And if I look at that direction, it also aligns to that direction. Okay. So we are now happy with our directions. And we can see that if we're going to create variograms, it will now create it in this plane with those angles of rotation up there. 80 degrees around Z, minus 18 degrees around X, and then 38 degrees around Y. Okay, so that's that. This part, we can then go back to our advanced estimation tool, and we can click on the next task, which is create variograms. We can now select the variable for which we want to create experimental variograms. Just for interest's sake, we can use all three, or we can only use one. I'm going to just use all three variables. We specify the zone or the domain which we want to create the variograms for. We have the option to transform, do a normal score transformation on the variogram, and we can also specify the type of variogram that we want to do: downhole, cross variograms, and directional. I'm going to choose those two options. I'm going to leave the cross variograms for now, just to save time. On the right-hand side of the window, we can specify the reference plane rotation. Here, what we will typically do is we will say read from 3D map window, and it will populate it with the angles we just determined with the 3D variogram maps. We can now specify the number of horizontal search directions. So I'm just going to specify, let's specify 6, the tolerance angles, and the range angles. We can also change if we want to. The vertical directions, we can specify that as well. I'm just going to make it 1 for the sake of this exercise. Okay. We could also specify a cylinder radius if we want to. Let's specify, make that 25, as our borders are 50 meters apart. Okay. Then we simply say calculate variograms. It should be done in a minute. Okay, so there it's done. And we can now go and fit our experimental variograms. So we move to the next step, fit models. Okay. You can see again, we can load an existing experimental variogram file, or we can save this one. So let's just call this one vgrams test. Just a little simpler name than the default. Okay. Then we can specify which variograms we want to show, and we can specify for which variables. Just to keep things simple, I'm just going to look at the variogram for gold. So I'm going to untick the. Let's click that. Sorry. Okay, so I'm just going to click the gold, and I'm going to choose display downhole, and then I'm going to first look at my downhole variogram for gold. Okay, as we've mentioned, the composite thickness was 2.5 meters. So let's make our lag thickness or lag distance about 2.5 meters. We can type it in, or we can use the drag the scale bar to change the lag. So that is our downhole variogram, and we can now auto fit it, or we can manually fit the variogram. I'm just going to use the auto fitting just to demonstrate. We can specify the number of structures. I'm going to say I want 2 structures, a maximum of 2 structures. You'll see in the beginning it loads 3 structures, so I can just remove one of them, then I can simply say run AutoFit. Okay, so it reverted back to 3 there. Let me just repeat that. So I only have 2 structures. Okay. Any case, so there is my auto-fitted variogram. With the downhole variogram, I'm interested in the nugget. So I can see if I look at my model parameters, we can also switch it on the format tab. But if I go to model parameters, I see my nugget is about 0.25. I can now click on lock nugget. I can go to format. I can say display variance, display model parameters, and I can format these graphs a little bit. So now we've determined our nugget, we now want to do our directional variograms. So what we can do is we can go back to this task over here, and I'm going to click on the untick the display downhole variogram, and I'm just going to click on my omnidirectional variogram, which is the first one. Just for this demonstration, I'm going to use the omnidirectional variogram just to keep things simpler. But we know that our borehole spacing was more or less 50 meters. So I'm going to slide my lag up to about 15 meters. If it's not exactly 50, I can just type it in. Okay. So that's more or less my my appropriate lag. I can then choose manual fit if I want to move these structures around like that, and to get a proper fit of my variogram like that. That looks pretty good. Okay, so I'm happy with my variograms. I can now commit them to my estimate. So we can go to save models. Under save models, we can say create candidate model set from the display. Click on that. It will give me my description, the variables, the zone. It says it's not for multi-variables. I can click on that, and I can choose commit to KNA and estimation. So that model will then be available for my KNA and for my estimation further down. You would have seen you could also import a model, but we created ours from scratch. The next task would be your KNA. As I said, unfortunately, we have only about an hour, so we can either schedule a separate webinar for KNA, which will be a short webinar, or you can look at Kathleen Hansman's webinars where she discusses KNA. I'm going to go to estimation now. Okay. With estimation, we have to provide a blank input model and obviously the output model into which we estimated the grades. My input model is going to be this model over here, which is just a blank block model. And my output model, I'm going to let's call it webinar. I think I've made another one, so I'm going to call it webinar 5. It gives us a summary of the number of samples and a summary of the parent cells in our block model. You can see there is an option to use dynamic anisotropy if you wanted to. We're not going to do it for this demonstration. Next, we need to define our estimations. Okay, so we are planning to do an ordinary creeked estimate, we want to do a simple creeked estimate, and maybe a inverse distance estimate. Our first estimate, you will see it's got a default description, and we can rename that over here. So let's call that gold_OK. The estimation type will be ordinary creaking. It is univariate. We're going to use parent cell estimation, but the option to do sub-cell estimation is also there. We can specify the cell discretization, which we would have been able to determine in the K&A, but we're going to leave it as the default 3 by 3 by 3. Under output data, there's three options. We can either output the estimates and the variance only, we can output some standard statistics, or we can output all the creaking statistics. I'm going to choose the last one, output all the creaking statistics. Then we can choose the sample variable, which is gold, and we can apply a prefix to it. So let's call it AU OK. Apply. And the zone is zone 1. If we want to see what fields we're going to produce with this estimate, we click on output field names, and that's the list of fields that estimate will produce. So the estimate will be AU OK _E. We will get the variance. We will get the number of samples used, the number of holes in which those samples occur, the weight of the mean, the correlation coefficient, the slope of regression, the variance of Z, the creaking efficiency, the Lagrange parameter, and the surge volume index. So that will be handy if we wanted to categorize our estimate. Right. The next step would be to create an estimate for the simple creaking and for the inverse distance. So we simply click on New. We give it a name, gold SK for simple creaking, enter. We're going to choose the estimation type as simple creaking. We will choose parent cell estimation. If you had a local mean field in your block model, you can use this option, and then it'll allow you to choose a local mean field in this drop-down list. We don't want to do that. We are going to use the local mean that's calculated per search volume. The discretization we're going to leave the same, and we can again choose output all creaking statistics. The sample variable, we have to choose the sample variables on the right. So I'm going to choose gold. I'm going to say add variable, and the zone, I'm going to choose add zone. Okay. Then we give the same prefix. Let's call it gold SK and apply. Our output field names will now have the prefix gold SK in front with the same parameters as the ordinary creaking estimate. Lastly, let's do our inverse distance. So we say new gold _IPD, enter. We are going to use inverse distance. We are just going to output the standard statistics for this. The sample variable again will be gold, and the zone obviously will be zone 1 with a prefix of, let's call it ID, gold ID, apply. So those are the inverse distance fields we will create. So we've got our three different estimates. You can see you could have added it for all the variables. I'm just going to do the gold estimate to keep it quick and simple. and we could have added all the domains if we wanted to. Okay. The next step will be to review the variograms. So we're going to click on Review Variograms. Okay. So automatically the gold ordinary kriging already applied the model we created earlier. If we want to look at that parameters, we can click on parameters on the right. We can see there's our ranges, our SIL, and our nugget of 0.25. Okay. We can also assign the same model to this simple kriging estimate. So we click on this, we go down here, we say apply variogram model to the estimation 2. And for the inverse distance, we don't need a model. We can also import a model, export a model, and clear the list over here. So we've applied our variogram models to our 2 estimates. We now can define the search volumes. As mentioned, there's been quite a number of improvements in the search volumes and what you can set here. So we're going to quickly go through the motions of defining search volumes. Okay. The first search volume is already applied, 120 meters by 120 by 120. Okay. We can see that the simple kriging and the inverse distance have no search volumes assigned to them yet. So we can quickly click on that and apply those search volumes to all 3 estimates. So let's go to that search volume. We can see we can give it a description. We can make it ellipsoidal or rectangular. I'm going to leave it ellipsoidal for this exercise. We can change the size of this ellipsoid. So I'm going to leave the 120 by 120 meters. I'm just going to make the Z a little bit smaller. I'm going to change that to 40 meters due to the orientation of my ore body. The rotation of my axis, I'm going to change that to the known rotation of my ore body. And then we can view the ellipsoid in the 3D space if we want to. So let's do that. I'm going to move my estimation dialog a little bit to the left, to the bottom. I'm going to go to my 3D window, and I'm just going to pick a location where I want to view my ellipsoid. So I click on that arrow, and I snap to some place where I can view my ellipsoid. So let's change that back to 30 minus 17 and view ellipsoid. So there's my ellipsoid. You'll see my distance has changed back to 120. So let me just quickly change that back to 40 and say view ellipsoid. And now maybe just have to switch off the first ellipsoid like that. Okay. So we can see, if I just move this down a little bit, that is my ellipsoid, and it sort of aligns to my borders. I can probably do a little bit better than that. But I think for this exercise, it demonstrates that you can change your search volume orientation, and you can also view it easily with the ellipsoid. So I'm going to leave it like that. Then the next step is to set the sample numbers. Okay. So the sample numbers, you will see we've got a minimum. I'm just quickly looking for my notes. We've got a minimum number of samples and an optimum per sector. Okay, so the naming is a little bit different from what we are used to in estima or estimate. They talk about sectors, where we would talk in estima about octants. And they also talk about maximum number of samples in estima or estimate, and here they talk about optimum number of samples. Okay. They are very similar, the optimum and the maximum number of samples, but they're not identical. Okay. In advanced estimation or co-creek, the underlying process which is called co-creek, the optimum number of samples can be exceeded in the following instances. If all the samples lying within the estimate cell, if all the samples lie in the estimate cell and it's more than the optimum number of samples, it will use all the samples in that block. Also, if there are sectors with less than the optimum and the minimum number of samples is not reached, then the samples may be added to sectors that have already met the sector optimum in order to reach the global minimum number of samples. And then thirdly, if the optimum number of samples per drill hole is activated, then additional samples may be added, which will cause the optimum number of samples per sector to be exceeded. Okay, so that's where the maximum number of samples in estima and the optimum number of samples in co-creek differ from each other. We can also see that we can add an ellipsoid size factor. So we can add a size factor and we can specify by how much we want to expand factor. And we can the ellipsoid, and we can change the number of minimum and optimum number of samples. Okay, so let's do that. I'm going to remove that one. Let's make a 2, a 3, and a 6 and add that. So it will expand the ellipsoid. Then we can also specify the optimum and maximum number of samples per borehole ID. So we can specify optimally we want to use 3 samples per borehole ID with a maximum of 10 for instance. So it won't use more than 10 samples per borehole ID to do an estimate. That might be a bit too much. Let's make it 5. The next task is setting the sectors. Okay. So this is again slightly different from the estima or estimate, where we talk about octants. So in estima and estimate, we talk about octants. In here, we talk about sectors. So they're more or less the same, but sectors are just a little bit more flexible. Octants, as you know, divides the surge volume into 8 equal parts, almost like an orange. But 4 parts are above the horizontal plane and 4 parts are below the horizontal plane. With sectors, you can specify how you want to cut up your surge volume. So if we click Enable Sector Method, we can specify the number of vertical sectors, and we can also specify to split those sectors horizontally. So if we want to have the same number of sectors as we would have done octants, we will have to specify we want 4 vertical sectors and we want to split this horizontally. You will see then we've got a total of 8 sectors, which is the same as the octants. We can specify the maximum number of empty sectors, And we can specify if we want to keep all of that in a block. You'll see there's also a couple of search constraints that we can apply for code creaking, which is not relevant here. Okay. Lastly, with search volumes, we can see how we're going to handle outliers. We can see we can choose the option to enable capping. And here we can specify the high value and the low values, the grade and the distances. Okay, so if you hover your mouse over that, it says the distance from the samples where capping or cutting is effective. Okay, so apply this to all values, we leave it as 0. And then we can also specify the low value capping or high value capping. We can specify to replace the value or to exclude the value. We are not going to use capping in this example, but the option is there. So now that we've applied our search volumes to our estimates, the last thing that remains is to go and run the estimate. So let's click on Run Estimate. It will give us a summary of the estimate. It gives us the holes that we're going to use, the input model, the output model. It will also create these webinar parameter files. So those parameter files we can use in the code create process, and we can repeat this estimation process using all those parameter files. You can see there's a couple of new parameter files like field names. That wasn't in the estimate process before. And we can also have the sample out file, which we can use if we want to go and investigate which samples were used to estimate which blocks. We can then just click on Run Estimation. So it's going to run the estimate for those 3 estimates for gold, and it should be done very quickly. The process will be reported in the output window. My output window or command window is at the back. It's just hidden at the moment. So let's just leave it until it's finished. But it should be finished any second now. Okay, so there we go. If we move this up a little bit, we can see estimation succeeded, code create complete. Okay, so we can quickly now go and look at our data. If you guys want to look at that, let's quickly close this estimation tool. We've got our drill holes loaded, so we can keep them loaded. I'm going to go to project files. I'm just going to quickly load my block model. Webinar 5, load. And let's quickly just color it by gold. Let's use the gold ordinary create estimate. We create a legend for that, apply. Okay, and let's just color our borders using the same legend. Let's switch on our section. And we can see there is our estimate. With our ellipse width, search ellipse width on the right. And we can look at another section. And we can see it follows the trend of our ore body. Okay, I think that concludes the run through of the advanced estimation tool.